Hi there. We talked today in class about systems of linear inequalities, and you'll find as we work through these notes that linear inequalities mirror in a lot of ways our systems of equations, with a couple of alterations based upon what we learned in 4.5 about graphing inequalities. Okay, so there are two sections to these notes. We dealt with solutions and then graphing a system of linear inequalities. Okay. The first section here, solutions, we're looking at the definition of a solution first of all, which says that an ordered pair is a solution to a system of linear inequalities if one of two things happens. First, if the point lies inside the shaded region, so this would be what you would use if you were looking at a graph, right? You'd be looking to see, is it in the shaded region? If so, cool, it's a solution. Okay. Or second, or I should say maybe and, because it would be true, but you would use this second technique if you were given the inequalities themselves, the actual equations, right, or the actual inequalities. If the point makes both inequalities true, when I plug that point in, do I get two true statements? Okay, so you use the two ideas based on what you're looking at. So if we're looking at a graph, we'll use the first one. If we're looking at two inequalities, we're going to use the second one. We're going to determine, does it make both true? Okay, so here we go. First one. We are asked to determine whether the ordered pair is a solution to the system of linear inequalities. We're given a graph, and so we're going to be using this first idea. The point has to lie inside the shaded region. And so for example 1 here, I'm asked, is 0, 0 a solution? Well, 0, 0 sits right there. Okay, it's not inside my solution area, inside my shaded region, and so this is not a solution to my system. Okay. And that's literally it. You then go to -2, -5. We go to -2, -5. That's located right here, which also is not inside my solution area, inside my shaded region, so it's also not a solution. We have -8, 2, which is located here, also not a solution. And then we have -3, 7, which is located here, and there we go. That is inside my region, and so this is a solution. Okay. And after we finished this in class, I had your classmates pick another point. I said, find another solution. What would be another solution to this inequality? And so that's going to be the challenge I pose to you right now. Try to find another solution. What's another point inside that area? Okay, and there are an infinite number of answers, so hopefully you have one in mind here. Other possible answers could be like -2, 2, -1, 6, 1, 8, -6, 6, right? There's an infinite number of solutions. All of those would be solutions to my inequality. In addition, this solid line right here, okay, are possible solutions. You could name, for example, -1, 5, right, would be another potential solution there. Okay. Unfortunately, you cannot name one of the ones on the dotted line, right? That's the one that kind of forms the shadow border of our area. None of these are possible solutions because this is just a less than or a greater than line, and not a less than or equal to or a greater than or equal to line. And so because it doesn't have that equal to component, you can't include any of those points, the ones that lie on that dotted line. Okay. Okay, so then next up we did these following examples, which is determine whether the ordered pair is a solution to the system of linear inequalities, which uses the second part of our definition of solution, which is that the point must make both inequalities true. And so if either one is proved false, you're done, right? It's already made one of them false, so it can't be a solution. It doesn't matter whether or not it makes the other one true. It has to make both of them true. And so if one of them's false, it's not a solution. Okay, so that's what we're going to do here. We're going to go ahead and plug in, for example, 2, 12. We have our x and our y. And so I'm going to be plugging in 2 here and 12 here. Okay, so my y is 12, which is greater than 2 times 2 plus 4. Plugging in my 2 into the x's spot. And 2 times 2 plus 4, 2 times 2 is 4 plus 4, which is 8. Is 12 greater than 8? Yep. So far so good, but we don't know yet that it's a solution. Because if it's a solution, it's got to also make this inequality true. And so you do have to check them both. Okay, so we're going to go ahead and plug that in. We have 2 into my x, we have 12 into my y. Okay. And 6, which is 3 times 2, minus 12 is negative 6. Is negative 6 greater than negative 7? It is. And so since both equations are true, this is a solution to our system of inequalities. Okay, so that's what we're going to do for the other 3. I'm going to go ahead and keep walking through them, but my challenge for you would be as soon as you feel like you are understanding the material, it might be now or it might be after the next example problem, but pause the video, try it on your own. Okay, try at least one of them on your own, even if you wait to pause the video till after example 3, and see if you can solve it on your own. That way you're again kind of evaluating, am I understanding this material, am I getting the process, or is this something that I need to come into class and then ask for further clarification, ask for further practice, or work after school, or whatever the case may be. Okay, but take that time to really practice on your own. Okay, so here we go, example 2. Again, we have our x and our y. And we're going to go ahead and plug these in, see if it makes both inequalities true. Okay, when I plug in my y equals 2 and my x equals 8, I get this set up. 2 is greater than, 2 times 8 is 16, plus 4, which is 20. And is 2 greater than 20? It is not. And so this is not a solution. Okay, and if you notice, I'm not going to plug it into the other one. Frankly, I don't care whether or not it makes the other one true or false. Honestly, within the context of this particular problem, as soon as you have one that's false, you're done. You know your answer. It's not going to be a solution. Doesn't matter whether the other one's true or false. Your answer is going to be no. It's not a solution. Because it's got to make both true. Okay, so we're going to do that again. We're going to go ahead and plug in 0, 0. We have 0 is greater than 2 times 0 plus 4. 2 times 0 is 0, plus 4 is 4. Is 0 greater than 4? It's not. And so you know this is not a solution to my system of inequalities. Okay, last one here. We have negative 3, 1. So I'm going to go ahead and plug in my x and my y here. Plugging in negative 3 into the x, 1 into the y. We get 1 is greater than 2 times negative 3 plus 4. 2 times negative 3 is negative 6, plus 4 is negative 2. Is 1 greater than negative 2? It is. So we're going to go ahead and check the other one now, because remember it's got to make both true. Okay, so when I plug in 1 into the y, negative 3 into the x, I get 3 times negative 3 minus 1 is greater than negative 7. 3 times negative 3 is negative 9 minus 1 is negative 10. And is negative 10 greater than negative 7? It is not. So this is not a solution, because it makes that second one false. Okay, so that's what it means to be a solution of a system of inequalities. 2 ways to check, depending on whether or not you were given a graph or you were given 2 inequalities. Okay, this brings us to our second section of notes here. Our second section of notes, we are asked to graph a system of linear inequalities. Okay, and so we have our steps here. Step 1, we're going to graph the 2 inequalities just like we did in 4.5. Remember to take note of whether or not they're going to be dashed or solid lines. Okay, once you've done that, you're going to determine the shaded regions for both inequalities, and then you're going to shade in dark the shared shaded region. Okay, what part of my shaded region overlaps between the 2 inequalities? Okay, and if you're looking at it and there is no overlap, then that means there is no solution. right? They've got to overlap. That's what you're going to shade in dark. Okay, so here we go. Example 1, we're looking at y is greater than negative x minus 2. Okay, so we've got our b, which is negative 2. And we've got our m here, which is negative 1. Okay, which means I'm going to be going down 1 and over 1 for my slope. Okay, so down 1 over 1, down 1 over 1. You only need 2 points to make a line, but if you want to do a number of them, that just kind of helps keep the accuracy of your line's track, right? It helps you keep your ruler straight. Okay, with this particular problem, we have a greater than symbol, which means this line, this inequality, is going to be a dashed line. So we're going to line this up and draw in that dashed line. And again, make sure it's clear that it's dashed, especially because my points down here are pretty close. You want to make sure it doesn't accidentally look like a solid line, so make sure there are parts where it's really obvious it's dashed. Okay, and so for this equation, we're going to go ahead and figure out what is the shaded region. We're going to determine that shaded region, step 2 there. Okay, a point not on the line would be like 0, 0. So I'm going to go ahead and plug that in. And when I plug in 0, 0, I get 0 is greater than negative 0 minus 2, which negative 0 is the same thing as 0, and 0 minus 2 is negative 2. Is 0 greater than negative 2? It is. And so we're going to shade the side of this inequality, the side of this line, where 0 is greater than negative 2, where 0, 0 is located. Well, 0, 0 is right here. So I'm going to shade in this side of the line. Now I want to do this really darkly. I'm sorry, let me rephrase that. I want to do that really lightly, I should say, because later on we're going to go in and we're going to darken part of it. So make sure you just very lightly kind of sketch where you know that line's shaded region should be. Right? Because we're going to darken in part of it and we're going to potentially erase the other part, just to make sure it's really clear that everyone knows what our answer is. Okay? Next one, we have y is less than or equal to 3x plus 6. So my b in this case is 6. And my slope here is 3, which means I'm going up 3 and over 1 because it's positive. So from here we're going to go up 3 and over 1. And again, you only need 2 points to create a line, but if you want to do a few more just to help maintain accuracy, you could. And then because this is less than or equal to, this is going to be a solid line when we connect these. Okay, so then same thing, we need to test a point. 0, 0 is also not on this line, so I'm going to go ahead and test 0, 0 again. And we have 0 is less than or equal to 3 times 0 plus 6. 0 is less than or equal to 3 times 0 plus 6. Okay, and 3 times 0 is 0, plus 6 is 6. And is 0 less than or equal to 6? It is. And so we're going to shade the side of the line, that solid line, where 0, 0 is located. Okay, 0, 0 is located here, and so we're going to shade in this side of that line. And again, do so lightly, because we're going to end up erasing part of it and darkening in the other part. Okay, which brings us to this last step, which is you need to shade dark the shared shaded region. What part do both inequalities shade? Okay, well when I look at this piece here, neither of them shade that piece. I have one of the lines shading this one. I have one of the lines shading this one, but here in this region, you notice we had both inequalities shading that region. Both times that we shaded, we covered this part of our graph. And so this is the part that I'm going to make sure it's really clear is my solution. Okay, and so you're going to shade that in really dark. Okay, and then we're going to go and we're going to erase the other two just to make sure there's no confusion from anyone looking at our work, that they are, so that it is clear to them exactly what we want our answer to be. Okay, that's our shared shaded region. Okay, So we're going to work through a few more here. Again, kind of the same challenge I posed with the previous set of examples where we were determining the solution of our inequalities or whether or not they were solutions. Is as soon as you feel like you might want to kind of try one on your own, pause the video, try it on your own, start it again so you can check your answer. Again, so you can determine whether or not you're actually understanding this material. Okay, so next one we have negative 3x plus y is less than or equal to negative 4. This one's in standard form, so you have a couple of choices here. One, you can graph in standard form, or you could turn this into slope-intercept if you prefer. Again, it's going to be your choice with this one. I usually just graph in standard form. Okay, so negative 3x plus y, if I determine my y-intercept, cover up that x, we get y equals negative 4. Here's my y-axis, y equals negative 4, right there. Okay, for my x-intercept, if I cover up the y, I get negative 3x equals negative 4. And if I divide that negative 3 over, like this, divide that negative 3 over, you get x equals 4/3, which is the equivalent of 1.333 repeating, right? So we're going to go ahead and graph where is that? Well, here's x equals 1, x equals 1.333, or 1 1/3 is right there. Just a little bit past 1, a third of the way past 1. Okay, because this is an equal to, this is going to be a solid line here. And then we're going to determine our shaded region. 0, 0 is not on this line, so I'm going to go ahead and test 0, 0. Plugging that in. We get negative 3 times 0 plus 0 is less than or equal to negative 4. Negative 3 times 0 is 0, plus 0 is 0. And is 0 less than or equal to negative 4? It is not. And so we are going to shade away from 0, 0. Here's 0, 0, so I want to shade the other side of the line, and remember, do so lightly because you're going to end up erasing part of it. Okay, next one, this one is in slope-intercept form, so there's my b. I'm going to start at 3. My m in this case is negative 2, which means that we are going down 2 and over 1. So down 2, over 1, down 2. And again, this is an equal to, so we are going to go ahead and make this a solid line here. And then testing that line, 0, 0 is not on that line either, so I'm going to go ahead and test 0, 0 again. Plugging that in, we have 0 is greater than or equal to negative 2 times 0 plus 3. So 0 is greater than or equal to negative 2 times 0 is 0 plus 3 is 3. Is 0 greater than or equal to 3? Nope. And so we are going to shade away from 0, 0 because that gave us a false statement. So here's 0, 0, so I'm going to shade over here. And again, make sure you do so lightly. Okay, so last step, what's our shaded region? Well, this one, neither of the lines shaded. This one, one of the lines shaded. This one, one of the lines shaded. And right here we see an intersection. Both lines shaded in this region. And so this here is going to be my answer. Okay, and then again, I would recommend going back and erasing the lights shaded from the other two places just to make sure it's really clear what our answer is. Okay, so we have a couple more here. Again, feel free to pause the video or stop the video and try them on your own if you feel like you want to give it a shot. Okay, we have y is less than 2x plus 4. Okay, so there's my b, which is 4. My m is 2. And so I'm going up 2 over 1. And this is a less than line, so this is going to be a dashed line when we connect this. Okay, testing a point, 0, 0 is not on that line, so I'm going to go ahead and test 0, 0. I get 0 is less than 2 times 0 plus 4. 2 times 0 is 0, plus 4 is 4. Is 0 less than 4? It is. And so we're going to shade in the side of the line where 0, 0 is. Here's 0, 0. So lightly shade in that side. Okay, next one, we have our b, which is negative 3. My m is negative 3 halves, which means I'm going down 3 over 2. So down 3 over 2. And then this is an equal to inequality, an equal to symbol. So this is going to be a solid line when we connect these. Okay, and so again, testing 0, 0, not on the line, so I'm going to test that. We get 0 is less than or equal to negative 3 halves times 0 minus 3. Negative 3 halves times 0 is 0, minus 3 is negative 3. Is 0 less than or equal to negative 3? It is not. And so we are going to shade for this one away from 0, 0. Here's 0, 0, so we're going to shade the other side of the line, and again, do so lightly. Okay, so where's your shared region? Neither shaded this one. One shaded this one. One shaded this one. Both down here shaded this region. And so this is going to be my answer right here. Just cleaning it up a little bit here. Okay. So we're going to do 2 more, and then the last 3 I put on there as extra practice if you would like. I did put the filled out answers on my website, so if you were wanting to practice those last 3 and check your answers, you could. Let's go ahead and take then a look at these last 2 here. Example 4, which is y is less than or equal to 3/4 x minus 2. There's my b. My m in this case is 3/4, which means we're going up 3 and over 4. So up 3, 1, 2, 3 over 4. Up 3, 1, 2, 3 over 4. And then this is an equal to symbol, and so it's going to be a solid line. Okay. Next up we have our b, which is our negative 3, and our slope, which is 3/4, up 3 over 4. So up 3 over 4, up 3 over 4. And this is a not equal to, just a greater than, so this is going to be a dashed line here. Okay, so testing our points. 0, 0 is not on this first line, the solid line, and so I'm going to go ahead and test 0, 0 for that one. We have 0 is less than or equal to 3/4 times 0 minus 2. So 0 is less than or equal to 3/4 times 0 is 0, minus 2 is negative 2. Is 0 less than or equal to negative 2? It is not. And so we're going to shade away from 0, 0 for that solid line that we plugged into up here. So here's 0, 0, so we're going to shade in just very lightly the other side of that. Okay. 0, 0 is not on the dotted line either, so I'll go ahead and test that for the dotted line. So we get 0 is greater than or equal to 3/4 times 0 minus 3. Okay. 0 is greater than 3/4 times 0 is 0, minus 3 is -3. Is 0 greater than -3? It is. And so we're going to shade towards the 0, 0 on this one, because this makes a true statement. And so on the dashed line, we're going to shade this way. So this one's a little bit trickier to see because there are only 3 regions, but when you just take them one at a time, you can find your answer. Here, only one shaded this region. Here, only one shaded this region. Their shared region is right here in between those 2 lines. That's their shared region, where they are both true. And just clean up the outsides a little bit. Okay, last one here. We have y is greater than 3x minus 2. We have 2y minus x is less than or equal to 6. Okay, so we have our b, which is -2, and our m, which is 3, which means we're going up 3 and over 1. So up 3, we're at 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. And this is a greater than, which means we are going to be a dashed line. Okay, for my test, 0, 0 is not on that line. So I'm going to go ahead and test 0, 0 into that inequality. We get 0 is greater than 3 times 0 minus 2. 3 times 0 is 0, minus 2 is -2. Is 0 greater than -2? It is. And so we're going to shade towards the 0, 0 there. Here's 0, 0, so shade in lightly that side. Okay, next up we have a standard form here. So finding my x-intercept, we have -x equals 6. So if I divided that negative over, we'd get x equals -6. So that's my x-intercept. Okay, my y-intercept, if I cover up that x, I get 2y equals 6. Okay. If I divide that 2 over, I get y equals 3. So I'm going to plot y equals 3. That's my y-intercept. Okay, this is an equal to symbol. And so it's going to be a solid line here. Okay, and then testing a point, 0, 0 is not on that line, so I'm going to go ahead and test 0, 0. We get 2 times 0 minus 0 is less than or equal to 6. 0 minus 0 is 0. And is 0 less than or equal to 6? It is. And so we're going to shade for that line, that solid line, towards the 0, 0. Here's 0, 0. So we're going to shade in that region. So what do they share? Neither shade that region. One shades this region, one shades this region. They both shade in here. And so this is going to be my answer. Right in here. Okay. And then clean it up a little bit. And there you go. That's graphing systems of linear inequalities.